Okay, let's talk about simplifying roots. And here is my super cheap definition of simplify. It kind of means to reduce the root in this context. So I'm trying to relate this maybe to reducing fractions in the sense that 2 over 4 is equal to 1/2. They're the same numbers, but one is reduced. One is the simplified kind of acceptable form. And let me show what that means related to roots. It's not like dividing necessarily, but we're showing things in a different form, an exact form that is conventionally acceptable, and we call that simple and simplified. So let's take a look at that. But before we do, we're going to need a couple properties. Let me just focus on one square root property, and that is the following. The nth root of a product AB, the nth root of a product AB, can be separated into the nth root of A times the nth root of B, or vice versa. You can go this way or you can go that way. And this is one square root property. It's related to exponent properties, and actually, if we were to represent this AB to the first power and say that this is the same thing as AB to the 1 over n power using the fractional exponent definition of the root that I showed on the previous video, then I could say this is the same thing as A to the 1 over n power times B to the 1 over n power. And you might recognize that as one of our exponential rules. And so roots and exponents are kind of the opposite of each other, or the inverse. One undoes the other. And so they follow the same rules. And if you look at it this way, you can say, oh yeah, this is the power to the powers rule, it's sometimes called. So let me show examples of using this rule to reduce, to simplify roots. So let me start with the square root example, just to kind of make it easy to look at. Suppose we had the square root of 20. Now, 4 squared is 16, 5 squared is 25, so this is somewhere between 4 and 5, and if we were to approximate it, we could do the root of 20 in our calculator and come up with some decimal number somewhere between 4 and 5. The simplified answer, however, is not an approximate answer. It's an exact answer. This is an exact representation, an exact expression, but it's not reduced. It's not simplified when we're talking about square roots. I still haven't quite explained what I'm talking about, so let me just continue. Notice that I can represent 20 as a product. I can represent it as 1 times 20. I can represent it as 2 times 10. But in particular, I'm going to represent it as 4 times 5. Now, I chose that specifically because 4 is a perfect square. So when you're breaking down a number and trying to simplify a square root, you're trying to find the factors that are perfect squares. This is one way to go about it, and kind of a nice way. Because of this property over here, I can say that we can separate this square root into the square root of 4 times the square root of 5. The square root of 4 comes out to 2 because 2 times 2 is 4. So this looks like 2 square root of 5. And this is what we call the simplified expression. It's the same thing. If you did 2 times the square root of 5 and got an approximate value, it is the same approximate value as the square root of 20. And in fact, these are the same exact representations, just like 2/4 is exactly equal to 1/2, but this one we call simplified. Simplified. Because we have taken the root of every perfect square factor of that number to begin with. And of course, this applies to higher order roots as well. Suppose we looked at the cube root of 16. think we actually calculated or showed that approximate value on an earlier video, but I want some sort of exact value that is simplified. So what I'm looking for is factors of 16 that are perfect cubes. 16 can be represented as a lot of things, just like 20. It could be 1 times 16, 2 times 8, 4 times 4. But if I'm looking for factors that are perfect cubes, the first thing I think about is 8. Okay, so I can re-represent this as the cube root of 8 times 2. And that's because I remembered that 8 is a cube, a perfect cube. 2 times 2 times 2, in fact, is the perfect cube of 8. So I'm going to take a next step to separate this product into the cube root of 8 times the cube root of 2. The cube root of 8 evaluates to exactly 2. And over here I end up with 2 times the cube root of 2. And this is my simplified result. Now there is a method, there is a way to do this if you didn't recognize right away the perfect cube or the perfect square. And you could use prime factorization actually to accomplish the task. And let me use that same example, the one we just did, the cube root of 16, to show this prime factorization way of doing things. So let me go back to this. Cube root of 16, and I'm going to do the prime factorization of 16. Let's see, 16 is 2 times 8. Let's say you didn't recognize the 8 as a perfect cube, so I'm going to keep breaking that down. This is 2 times 4, and 4 is 2 times 2. So, represented in its prime factors, the cube root of 16 is the same thing as the cube root of 2 times 2 times 2 times 2. Now I could, what I do is I just put a circle. I say, oh look, there are 3 2's. That means 2 is being cubed. I can circle that and say that the cube root of 2 is 2. And what I'm left with is this part, the cube root of 2. But let me separate it. Let me say that, okay, this is the cube root of 2 cubed times 2. This is one way to do it. I could have called it 2 to the 4th power, but I didn't want to call it 2 to the 4th power because I'm looking for some power that matches this outside index. Now I'm going to separate it into the cube root of 2 cubed times the cube root of 2, this guy right here. The cube root of 2 cubed is 2. So indeed we have the same thing. 2 times the cube root of 2 is our final result. Same as that. It is a little faster if you can recognize the factors that are perfect cubes or the factors that are perfect squares. It depends on the order of the root that you're taking. If you can recognize those factors right away, then you can break this down a little faster. But if you don't, take it all the way to the prime factorization and go from there. Let me show on the next video a few more examples of simplifying roots and coming up with different ways to do it. Okay, see you on the next video.